Personal protective equipment is an integral component in injury prevention in various industries. Safety glasses provide a barrier between the eyes and hazards, including debris, radiation, and chemicals.
For this project, we have developed a pipeline to determine if an individual is wearing safety glasses, regular glasses, or no eye protection before starting any work that has potential to harm the user's eyes.
Safety glasses and regular glasses share many similarities, and there are many different types of each. It is also common to see both types and/or no glasses in the same environment.
Implementing deep learning image classification techniques assist in safety compliance, providing real-time safety protection, and can alert users to unsafe procedure or machine operation.
Our model is meant to promote workplace safety, so to demonstrate that, we'll display its performance in a workplace setting. Let's visit Chris at the lab. Here, we see the model detect and track Chris's face. Now, with safety glasses on and verified, he's ready to work with whichever chemicals or hazardous materials his research requires. The detection model is also robust to Chris turning his head, and the classification model keeps up with the skew input. The model was able to correctly identify a lack of proper safety equipment and warn Chris, leading to a safer workplace environment. So you might be wondering, what about other types of safety glasses? Let's check out what Connor's up to. Connor is at the control console for a laser tube cutting machine. Before operating the machine, Connor puts on special laser protection glasses and the model detects the switch. Although these types of safety glasses were not present in the training data, the model has generalized and can still make correct predictions. Here we also demonstrate model robustness to certain conditions such as corrective eyewear underneath standard safety glasses.
We leveraged YOLO in our pipeline for detecting faces in the input image and removing unnecessary background information. Our YOLO model has been fine-tuned for faces with data from the Google Open Image dataset. Once YOLO has detected and classified the face, it is cropped and exported as a tensor into our custom classifier architecture. Our custom classifier architecture utilizes transfer learning methods by leveraging pre-trained features from AlexNet, which is then fed into our CNN architecture, which consists of one convolutional layer followed by two fully connected layers with ReLU activation to introduce nonlinearity. The model has three output neurons representing the three distinct classes. Our classification training data consisted of stock images collected from various datasets on Kaggle.
After fine-tuning on labeled human face examples from the Google Open Images dataset, our YOLO detector scored an accuracy of 73% on the holdout data. However, the YOLO detector was able to correctly identify 14 out of 14 safety examples, so we proceeded with the pipeline.
For the classifier, we scored an accuracy of 87% on holdout data, similar to the stock images used for training.
Specifically, the model produced class accuracies of 80% for glasses, 95% for no glasses, and 85.7% for safety glasses.
We also test our model on unseen sample images to better represent real-world deployment. The model is able to classify correctly 6 of 7 normal images and 5 of 6 where the head is turned away from the camera.
By generating class activation maps, we can see which areas of an image are most important in correct classification. Initially, AlexNet extracts features such as edges as seen around glasses frames. As we move deeper into the network, we can observe the eye region becoming more important in prediction. Finally, the custom convolutional layer determines that the upper eye and eyebrow area is most important for the glasses class. When an individual is not wearing glasses, we can see the network activation is focused more on the face as a whole. This makes sense as we do not have clear prominent features to focus on, such as the frames. A human's intuition might recognize the same pattern. Lastly, the safety glasses class produces interesting activations, which are somewhat a combination of the two previous activation maps. While both of these test images were correctly identified, they have much different activation maps within the classification network. The transparent frames on top produce higher activations near the bridge, whereas with darker frame glasses, the network focuses on the nose and under eye area. This could be due to most glasses having solid frames below the lenses, and the network learned that solid bridge safety glasses most likely will not. Class activation maps can also be interpreted for better understanding of incorrectly predicted classes. In this harder test image, the model predicted with high confidence that Chris was not wearing any glasses. However, it's obvious this is not the case. With respect to a no glasses prediction, we can see the model has high activation around the center. For a safety glasses prediction, the model deems the respirator most important, ignoring data that would inform about the presence of eyewear. This would appear to be a point of failure for the model, though it is not too surprising since conditions like this did not appear in the training data. Another technique we use for interpretability is visualizing neuron maximum activation. Here, we use random noise and gradient ascent with regularization to produce images that would maximally activate a target neuron. In this case, the output neurons representing our three classes. It's easy to notice some distinct patterns in these generated images. For glasses, we can see closely packed round shapes, likely relating to glasses frames around lenses. In the middle no glasses map, if we look closely we can see eye-shaped blobs, and perhaps some with noses. Lastly, the safety glasses neuron responds well to an ellipsoid-like distortion in the upper two-thirds of the input image, much like what you would expect to see with large protective eyewear. Here, with some feature maps visualized, we can see making this shape with hands can easily fool the network. So there you have it. Thanks for watching our presentation. Hope you enjoyed and maybe even learned something.